In this work, we present automating multi-turn cable routing on the NIST fixture board with a bimanual robot and caging grippers. In settings such as wiring for vehicle manufacturing, server routing for data centers, and the configuration of electronic infrastructure in industrial settings, automating the routing of cables is a fundamental challenge that lags behind other components of assembly line automation. Achieving a reliable routing is challenging due to complex cable dynamics, fixture constraints, and the need for slack management. In our approach, we begin by framing the cable routing task, where a user specifies a desired cable routing sequence for a particular 2D fixture setting, and the robot plans and physically executes said routing. In our work in particular, we adapt the NIST Task Board 4 to create a configurable cable routing setup in which the robot interacts with C-clips and peg fixtures to route a cable between sockets. For this setup, we introduce motorcycle, multi-turn optimized trajectories for ordered routing of cable yoking and cable loop execution. Motorcycle emphasizes a bimanual approach to the cable routing problem, in which one arm is used to route the cable while the other manages cable slack. We argue that this management is essential to the cable routing task in order to prevent tangling with the environment's many fixtures and to control the cable's variable dynamics. At a high level, motorcycle consists of 3 stages: cable tracing, waypoint planning, and execution with a bimanual Yumi robot. As input, we provide a top-down RGB image of the board with a cable fixed at one end, the positions of each clip on the board, and a user-specified desired routing. We use handloom, an autoregressive cable tracing model, to determine the path of the cable. Since handloom requires a starting pixel to begin its tracing, we first conduct a pixel search around the starting clip. After running the model, we use the output trace to identify grasping points for each arm that avoid collision with any fixtures on the task board. Next, we plan the desired routing as a series of waypoints around each fixture. By computing whether the routing should follow a clockwise or counterclockwise trajectory, we map waypoints around each fixture accordingly. Finally, it's time for the ABCs of execution. We begin by using the A-star algorithm to plan paths between waypoints while avoiding collision. Extrapolating from this path, we then create a trajectory for the second arm to follow. To allow for sliding and pinching motions, both of which are used during our routing, we modify caging grippers used in previous works to include a horizontal crossbeam to retain the wire. To evaluate the effectiveness of our method, we define 3 tiers of routing in increasing complexity ranging from 3 to 5 key points. Evaluating across these tiers, we are excited to report that motorcycle significantly outperforms a single arm manipulation approach, achieving an average success rate of 84% across all 3 tiers. Thank you for watching. To learn more, please read our paper.